Hi, my name is Leon. I'm a student assistant at the Digital Design Unit at TU Darmstadt, and today I want to talk to you about mesh modeling and how we can use mesh model surfaces for 3D printing and for 3D printed formworks. There are several examples we can find in the research that already use 3D printed formworks for concrete or plastic casting. As seen here by the ETH Zurich, there we can get a high complexity through 3D printing in the concrete elements. And this is only possible with additive manufacturing. Another example of this elastic formwork that is also 3D printed and has a high complexity, and with this we get a huge design freedom, and with this we are able to design whatever we can imagine and cast it in something really solid. In this tutorial we want to take a look at an example by the Crate team. They've used some mesh modeled surfaces to create formwork for concrete casting. And in this video tutorial, we want to highlight some of those examples, rebuild them with Grasshopper in Rhino, and then prepare them for 3D printing in order to get something like this. This is a 3D printed formwork, and that we can pour some concrete or plaster into and get a solid object with a high complexity on the front side as well as on the back side. So without any further doing, let's start into our Rhino file. We prepared some files for you that you can download. So this is our goal, what we want to reach, and we will separate it in something like 3 different parts. One part will be the surface creation in front, where we have 3 different methods and how to create different surfaces, as seen in the example by Crate. And then there's one part about the back surface, how we can create this and why we have some zigzag or wavy form at the back. And the third and last part will be about 3D printing. How can we prepare this file for 3D printing, and what do we need to consider if we want to print it, what are limitations and what's the fastest way to do it. Therefore we will slice it and generate the G-code out of it so that we could directly send it to our 3D printer. Let us start with our Grasshopper file here, and it's somehow nicely structured into the input part. These are sections where you can adjust something. This is the part where you can manipulate some values, adjust some certain things, and here have the 3 different typologies or different methods we want to explore. And here are the outputs, things that we get out of this definition. And here down here you will find the Grasshopper definition coming from these inputs to these outputs through different steps. Everything is labeled here, so you have the possibility to go through the script, and in some parts we will do it as well to explore what is happening and how are we able to create such surfaces. So the examples we want to explore are the example here on the down right. This is a remeshed surface. Then we have this on the upper left here, where we can take an image or any somehow picture and an attractor curve to manipulate the surface and to give it a certain depth. And then we take a look at this one here, which uses sinus curves to manipulate the surface and to get a certain pattern to it. We will start with the sinus wave. First thing you will need to do is go to the general settings. Here you find general settings like the height, our wall thickness. This is something for 3D printing. We'll take a look later. And some cutting geometry that will somehow roughly cut the model to precise size. And right here you can select if you want to create a sinus mesh, do some remeshing or image to mesh. And as we start with the sinus mesh, we keep this here. And over here in our Rhino file, we can see that we have some 3 curves, and a 4th curve lying before. And this is because if we take a look into our inputs for the sinus mesh, we can see we have some input curves. Those are the curves here that will span or that will loft a surface. The attractor curve is this one here. We have some UV count or resolution of the surface. These are 3 attractor points on the surface. Some other things we can adjust. Let us take a look at it, and to see what is happening, we can turn on the preview over here, taking a look at the front surface. So this is what we get, and now let us take a look at how do we get there. If we start here, we see that we start with our input curves over here. That will create a loft and a basic surface. So if you want to change the surface, you can easily manipulate it with this control point, or use any surface you can create and load it in here into the input surface. Take this as baseline. What we're now doing is scaling up a bit. This has something to do with creating the formwork afterwards. It doesn't need to bother it this way. It's just information that we scale it a bit larger as the original to make sure that we can cut it now afterwards precisely. What we're doing here is creating surface points. So we're dividing the UV count or the resolution, dividing the surface in several points, like a point grid lies over the surface. And this gives us some basic information about, or some points we can manipulate with the sinus. And down here you'll find 3 attractor points that will come here on the surface. You can see them here. And if we go up here in the manipulation or in the input mode, we can drag and drop them and they'll move along the surface. So this you can use to adjust later or afterwards the attractors on the field, and you will see what will happen in a few seconds. We're merging the distances, so we're measuring the distances between our points over here. So these are base points to, on the one side, attractor points that we can manipulate via this drag and drop fold over here, and our attractor curve that we can see over here, and use this as another way of manipulating the sinus curves. What we're doing is we're taking the distances, putting it up together for each point, the distance to the attractor curve and to the attractor points, and taking the lowest value to manipulate with the sinus sequence. So we're multiplying with the sinus sequence, and you will see it in a few seconds. If we go a bit further, you can see here now that the points have moved. So what we have done is we have taken the distances as an amplitude for the manipulation of the surface points, or as a vector. So we're moving them along the normal vectors of each point. So we have this surface grid, and we take each point, take the normal vector of it, and manipulate it or multiply it with a certain value that is over here multiplied with a sinus. And therefore we get this wave-like form. We can then adjust the amplitude of it. So what's happening here is just we're creating a grid or a surface out of this point grid. And then we have the surface over here. Now let's take a look at certain aspects. We can either change the sinus sequence. It should be, so if we increase it, there will be more and more higher frequency, and if I turn it down, it will be quite less. So I thought sticking to 0.6 is a good value, and then we can take the sinus amplitude. This gives us a control over how high the waves are. So if I put this value to something like 2, narrow, and if I turn it up to 6, you see it's a really high waves. Yes, still stay with 3. So as you can see here you see some points which are or represent the attractor points, and if I now move the points over here, you see how they are moving on the surface, and how with this you can manipulate the behavior of the waves on the surface, as well as with the attractor curve. So you could move those points over here and see how it behaves And this gives you the possibilities to explore this way of designing with it. And this gives you the possibility to design with the sinus curve and attractor logic, different design variations on the surface. And next we want to go to the remeshing. This is quite an easy task. You see here the script is quite short, and we change from here from the sinus waves to the remeshing, and have also 3 basic curves as an input. So you see the inputs over here. So you're seeing the parameters that you can adjust with the remesh is you can change the input curves or the way you create a surface, and you can manipulate the edge length of how long the edges will be. So this is quite similar. The remeshing is quite similar to the sinus waves we have looked on earlier. You can take the input curves to create a surface, as you have seen already, but you can also use any other surface. We scale it up in order to have better access or better possibilities with the formwork afterwards, and then remesh it. And here you can see, or don't see that much. You can see some triangles maybe. But we'll take a look at it in a few seconds, where you can see how it's remeshed. But here we use the edge length in order to define how large the triangles will be. And the try remesh function is a basic function out of Grasshopper, nothing special. And yes, now we are somehow deconstructing the mesh into separate phases and creating a surface again out of it. This has something to do with thickening the mesh afterwards, or the triangles afterwards. And as you can see, you can now see the edges of the triangles and how it's remeshed. And if you now change the edge lengths maybe to something like 55, you see how they get much longer. Or if I go to 20, how it's even more precise representation of the surface below. But we stick something with 35 to have a certain abstract pattern to it. And here you can explore a lot with the underlying surface. So it makes sense to somehow make it adjustable in Grasshopper. You see nothing is happening now. This is because, as I already told you need to activate it here again, the data dam. And now see here how it's been updated. And that's all the magic behind remeshing. And as a last tool, we show you the image to mesh. That's maybe most complex of those 3 methods. Therefore we go to the general settings and select image to mesh, and here you can see how there are a lot of adjustments possible. We use this baseline curve. If we start quite simple here, to extrude it and to create a basic surface. We did it in the other 2 examples with 3 curves, just of creating some surface. That's all we do here, and we use the height also defined in the general settings. We scale it over here. You see it's already the scaled surface. Then we are dividing the surface as we did with the sinus mesh. So we have a point grid over here and the UV count. So this gives us somehow the resolution of our surface afterwards. So we can increase the number to something like 60, and we'll get a lot of points to it, but have much more finer surface at the end. Or go down to something like 20, where it's really a rough image. I would recommend to stay something around 50. At first we do something similar to the sinus wave. You have some attractor points and or in this case attractor curve. You see this purple attractor curve over here. We measure the distance in order to manipulate the surface. And what we want to get is something like, as you can see here in the 3D printed version, we have something, a curve picturing out of here, or like stencil pushes out of the uneven surface at the surrounding. This is the attractor curve. It follows the same logic as the other one. And now here's the exciting part, the image sampling. And if we take a look over here, we can see that I can put an image over here. By double clicking, I can select an image out of a library of certain patterns or certain images, and that I can use to manipulate it. So we'll stick it first to this image and can change it later on. So we're using this information and the black and white information and the color information of this picture in order to manipulate the points over here. So every point of the surface gets a certain value according to the image data. And we're giving it an amplitude, so you can imagine or can adjust how much effect does this image have to the overall structure over here. So this will be something like the finished result. We have this attractor curve stenciling out here in the middle and some irregular shape according to the black and white image, or according to the image over here that surrounds the curve. Yeah, down here. So this is some manipulation. There are some amplitudes where you can adjust how much effect does certain aspects should have. Over here, or in case over here, you can at first set the attractor curve or manipulate it. You can adjust how much deviation there's in the surface from start to finish, and how much angle somehow is in it. And then the strength of the attractor curve, how much should it stencil out. And if you go down here with something like 2, you should see the fact that that's not that hard pushing through. Going here to this value, if we set it something to 1, see how this is really not pushing the image that much through. And if you go high to 7, see some really increased or high depth in the image. I stayed with 4, but it depends on the image you have. Okay, we still see here some extreme points, so maybe go down with 3, and I think that's quite nice. And yeah, so we're then, I call it weights, so how much weight does every aspect has, and here's certain combinations you can adjust. So at one point you can select here image and attractor, so we're using the image data and the data of the attractor point. You could also only use the image data, so you see the attractor curve has no effect, or only the attractor curve. So this gives you some design freedom in order to design how you wish. I will stay to the combination of both, as I find it quite interesting. Yeah, so we're giving every point a value of how much it should move, and then multiplying it with normal vectors of each point, as we already did in the sinus wave aspect. And here we have a general amplitude, so we can increase the general height or variation of this, and you can find the general amplitude, surface amplitude over here. So if I multiply it with 4, everything is more extreme somehow. So this is the manipulation of the surface, and then there's some part that we mainly need for the formwork creation that allows us to move the whole segment in the y direction. And now we're just creating the surface out of the surface grid points you can find over here. So out of this grid point we create the surface. And with this, we have given you 3 possibilities on how to design your surfaces. I think these are quite interesting ways or new ways of manipulating and designing some surfaces. And in the next step, we take a look at how to create the formwork around it. That we not only have like the front face, but also here the surrounding faces around, as well as the base plate. Okay, so in the next step, we want to take a look at the back surface here on our formwork. You can see those blue sections here at the end of this curve. Those are connection interfaces between several elements. So this is a possibility to add several elements together and have a way of how to interlock them. This is not mandatory, but might be a nice design part, as well as gives some stability to the formwork. And here the line on the back, the green line, is some guide curve for our zigzag or wave structure at the back. So let us take a look on the back surface and on the backhand side. Here in this grasshopper script, you can see we have taken a look at the sinus wave remeshing in the image to mesh, and here you can see back and side creation. Here you also see the settings we have possibilities to design with, taking the back side curve as an input. So this is the curve on the back, and the connection interfaces are the left and right curve of this formwork, and at this point we will get later. So let us take a look at this file over here. We start with the curve and divide it into several points in order to manipulate them. The amount of points is given up on here in the settings, number of extreme points. So how much extreme points you want defines in how many points the curve gets divided, and as well how high the amplitude is. And what this is now doing is it takes certain points of the curve and shift them in a certain way. So there's every third point that is shifted and then moved in a way. In this case, see they are moved perpendicular to the curve in order to create this wavy form, and then we weave them together and interpolate a curve between those points. Right, so these are the extreme high points, these are extreme low points, so to say, and this is the way how we can manipulate them. And if we take a look back into our settings over here, we can set the number of extreme points maybe to something like 5, and we'll see, okay, we have 1, 2, 3, 4, 5 extreme points now on this curve, as well as the amplitude. This is how high or how much the points get shifted away from the base curve, and we start something like 4 and we go to 7, we see, okay, it's much more of a zigzag form. And now here comes the point of the digital fabrication into account. We need to, well, what this is good for is if we fill our formwork later on with some plaster or some concrete, we get some pressure because of the volume of the element. So this will split up over here and extend. And with the zigzag form, we can prevent this somehow and give it more stability in itself. So this is in general why we are doing it. But if we take into account that we want to 3D print it, we need to consider on how the print is moving. We will take a look at it a bit later if we go to the slicer and how the extruder is moving. But the sharper the corners and the more change of direction, and the slower the process. So if it goes a straight line, the extruder is the fastest possible way. And if we take long sections and high zigzag with high amplitude, the extruder will drive in this direction, needs to slow down and drive in the opposite direction. And this is quite slow and will increase the printing time of our print. So we've tried to find a solution in this case where the change of direction is not that high in order to get higher printing speeds. Okay, after that is done, we also take the connection interfaces over here and join them together as one curve, and then we extend them over here. This is something to do as well as the scaling in the first sections in order to have a precise formwork at the end. And then we do some fillets. This will round the corners and also will increase the printing time and will provide us a smooth transition between the connection interfaces and the back curve over here. And you can adjust the fillet radius in the section over here. Then we have this back side and we'll extrude it and have this extruded, just a linear extrusion to it. Here starts the trimming process. I will just turn off this interpolated curve. We have the back surface over here, and we somehow need to cut it here so we have one continuous path that we can follow throughout and don't have something like a dead end at some point. So what we do is just splitting our back surface with our front surface, and now you can see why we scaled it up. So we have a clean cutting edge over here where the two intersect, and this will provide us with some trimmed edge that also follows the contour of the front surface. Then we thicken the surface. Here's a special component that is not part of the regular grasshopper components, but is part of the pufferfish plugin. It's called offset surface, and we'll later on also find offset mesh, and this provides us with thickening a surface in both directions and also making it solid. And coming to the thickness, we will discuss the point later on, but you can adjust the wall thickness in the general setting sections over here. The thickened back surface over here, so you know these had a certain thickness and is a solid object. And we will continue with the base plate. Therefore, we take our back surface and create a bounding rectangle around it. And this is an easy way to generate the base plate somehow. We will scale it to have some bit of insurance. It will also cover the front surface if there are any deformations we can't see in the back surface right now. I'm using this as an input. Then we'll trim this rectangle on both sides. See, okay, now we have the surface that is trimmed to the back contour, and we will also do it with the front contour. In this case, you see, okay, here's where the ejector curve of the image to mesh surface was, and that's why we have this bump over here, but it follows the contour, and at the end we just extrude it with the wall thickness and generate us a base plate over here that directly follows the contour. And don't wonder, there's some edge standing over here, but that's no problem at all. Okay, perfect. So we somehow quite rushed through the back surface and the base plate, because it's quite simple. Try to explore, or you have the possibilities to explore with the back surface over here, creating the zigzag. And in the slicer we can see what are the benefits somehow of different zigzag shapes. You can also increase the points. We can do this quite quickly by, like, if we increase to 9 somewhere over here. See, okay, these are much more, but then there's a lot of change of direction, which will slow the extruder down, or the 3D printer. Okay, so we leave it like this, and this will automatically get updated. You can see it also over here, the base plate as well. And we have the front surface. But what we want to do now is only just thickening the front surface. Therefore, we go to in this last part over here, thickening surfaces. We have a filter over here where you can select, or that automatically selects, okay, if we do the front surface, so the image to mesh surface, the remesh surface, or the sinus wave surface. And there are just 3 different methods of how to thicken the surfaces with some minor adjustments. Here you can find the offset mesh surface for the remeshed surfaces. We use this component, also part of pufferfish, that you can download via Food for Rhino. Yeah, this thickens us the front side as well. As you can see now, we use the wall thickness over here, giving it 0.8 of thickness, 0.8 millimeters. And here we are moving it a bit. This has something to do with the solid union we are performing afterwards. There might be some issues where it's useful to adjust this value to somehow push the front surface a bit more into the formwork and create a solid union after it. But now at the end, we bring everything together. So thickened front formwork, thickened backside, and the base plate, and merge it together. And here is a placeholder for the data dam. I put it up in the setting section where it will perform the solid union and get you the formwork out of it. So we can see here, here's this data dam. If you activate this one, it will load for some seconds because it's performing a solid union. Then we should get a result here out of formwork when we activate the preview. Perfect. Now we have here the whole formwork with all the adjustments we've done. So we have the zigzag at the back, we have the connection interfaces, and the seamless transition to the front surface, and we get one close pre-wrap out of it. There might be parts where you could get to some problems. I will show you one part where I was facing some difficulties, but they are not that important or that dramatic. Because if you go to remeshing, we're using a different method of thickening the surfaces, and if you want to activate this again, or activate the data dam, you see the front surface is missing. This is because the back surface and the base plate is a B-wrap, and the front surface is a mesh. But you can just simply activate it over here. Everything else works. You have the front surface over here, and you can work with this. So it's just 2 separate elements, but this shouldn't bother you any further. Perfect. So now we have learned how we can create with 3 different methods some front surfaces, and also creating a back structure to support the overall structure and even design the back surface. What we want to do now is prepare the model for 3D printing. What do we need to consider? What are difficulties? What are settings we need to face or to do in order to get the best 3D printing result? For this case, we take a look again at image to mesh and activate this here again. And we can turn on the front face. So what we have here now is our formwork, and we'll go now to bake and bake it on the base layer, and should now have a baked geometry here in Rhino. So we can turn this off and even close Rhino for this, close Grasshopper for this point, and now have this file over here. I was talking about wall thicknesses, I was talking about printing speeds, and this is some things we can consider while designing for digital fabrication. These are elements that improve or increase the printing times or make it more efficient, the process we are planning to do, by still giving us a huge design freedom. It's just some minor choices that somehow have a huge effect on the manufacturing side that we always try to think about while designing. So why do I use this 0.8? This is because we have a special 3D printer that we take a look in a few seconds. Other things to concern, there's not much to do to prepare it for 3D printing. This is quite a simple process. We just take the geometry, select file, export selected. There's some things he will ask us. So this might be at one hand the resolution or the tolerances. I've put it down to 0.1 millimeters as a resolution. Some feedback about how we want to save this file. It looks something like this. So it tells us, okay, there are 620,000 triangles, and we'll have something about 31 megabytes. But it's totally fine. We want to save it as binary, and just press OK. And now we have generated an STL file that is ready for 3D printing. And some things I want to talk to you about the slicing, I will do in the Prusa slicer that we take a look in a few seconds. Okay, coming to the last part, we have this Formwork over here, and we exported the STL to it, and now we want to slice it in the Prusa slicer to prepare it for 3D printing. Therefore, we'll open the Prusa slicer. What you see is the printing bed over here, some settings in this section, and yeah, let's walk it through. The first thing we'll do is we go to data, go to import and import configuration. We go to the Modex printer setup that we provide here to you, because we're using some special 3D printer that has quite a huge printing bed to it. We have now a lot of options we can adjust. But maybe the first thing we'll do, we take our STL file over here and take this and just drag and drop it into the Prusa slicer. And we now see, okay, the dimensions are something about 15 centimeters. So the print bed is quite huge. You can see that it should be 60 by 60 on the base. And now we have a 3D model here, and we get now to the printing settings. So first I'm over here, I activated the expert mode over here on the right, that have a lot of things they can adjust. By importing the configuration file, a lot is already set. So we can adjust something here. What we will do is activate the spiral vase modus over here, and this I will show you in a second what we'll do. And so we have a special printer. We go to the printer settings, to the extruder 1, and do a printing size of 0.8 millimeter, and because we have quite a thick printing nozzle. So, and now we can go to slice now, and it will calculate how it will print, and you should see something like this. So what we see is our model we've created, and you can now see some sausages going around here. These are the printing path of the 3D printer, and we can visualize this as well. So by slicing, we take our model like this and separate it in a lot of really thin layers that are about 0.2 millimeter thick or high, and we slice it in a lot of sections, and then the 3D printer follows this contour each and every layer, and therefore builds it up in this direction. So you can see here it's something like 750 layers. This is how the printer will follow it, and we take this layer for example, and here we can see how in this layer how he proceeds. You can see here the printing nozzle, and see that we have only one line. This is because, and here comes the wall thickness of 0.8 millimeters back at this point, because our printing nozzle, so how much plastic is coming out at the printer, is 0.8 millimeter thick, and by creating a geometry that has the same thickness, he will only places one continuous path along this contour. So we don't have wall thickness of one line of plastic that the printer prints around. And because of the spiral race modus, he doesn't finish one layer and goes up to the next layer and prints this one, but continuously flows in like a spiral around and around and around. Therefore, it is important to have no dead ends or a continuous flow of geometry. And we can see now how he follows like this path of the contour. And you can see a lot of different other informations over here. Up here in the left top, you can see the printing time. It's something around 3 hours. You can see how much material it will be used. It's something about 70 grams of plastic. And down here you see the G code. The G code is information that the 3D printer needs in order to move his machine head. You probably learned about every machine works with some sort of G code that tells the machine what to do. And it's maybe something like move from point A to point B, or do a right turn, do a left turn. This information is stored over here. And we can somehow validate that everything seems fine. We can see the base layer is something like a zigzag structure and also 2 layer thick. And we have this outskirt over here. This is in order in the printing process to provide good material flow and then do some adjustments from the height of the printing bed. And if we think this is fine, we can then go to the export G code over here, and let us export our G code into the file, and this is what we can then give the 3D printer in order to print this file. One thing to mention over here is I've talked about wall thicknesses and printing speed, and you can see somehow what I mean with no sharp corners, because this is somehow quite good flowing form. But if we can see in such corners over here with the radical change, he needs to slow down a lot, especially in such 90-degree angles like this one here. The extruder needs to slow down, and therefore it is slower. So we improved the time, and also if there's a zigzag with a higher amplitude, it also means more weight that needs to be traveled by the extruder and more material is used. So with this, you should have learned everything from creating surfaces in Rhino to creating a formwork out of this surface and preparing this surface for 3D printing, and then also slicing the model and generating a G-code out of it. If you want to take a deeper look into what 3D printing is about and deeper knowledge and understanding how a 3D printer works, there are a lot of good tutorials on the internet you can find. We will link you some down in the video description below that you can find and follow, and with a lot of information. It's a topic we can especially go very much into detail, and it's a lot about experimenting. It's about the composition between material and machine, and there's a lot of adjustments. In this video tutorial, we wanted to show you a way from creating surfaces and use these principles in order to have huge design freedom, maybe in the field of architecture, but also in some other fields. Advantage of additive manufacturing is the huge design freedom, the possibilities to explore new forms, new surfaces that would not be able to realize in different materials or in different environments. We can use this as a base or as a possibility to design our environment and therefore design other things. Because if we go back to the pictures I've showed you at the beginning of the video tutorial, these are possibilities in a solid material, in a casted material, that would not be possible without the use of digital fabrication. And in this case of digital formwork or digital fabricated formwork. Thank you a lot for paying attention to the video. I hope you learned some points, and feel free to ask any questions if you have some. And goodbye.